Good afternoon. My name is Brad Ennis. I'll be presenting for the red team. My teammates are Austin Neely and Ben Kegley. I will be speaking today mostly about the filter wash station in regards to the frequency response experiment and its modeling. Quick summary of what I'd like to talk about. Quick background on the system itself. I'm going to show you some previous work, specifically the steady-state operating curve for the step response. Then I will speak briefly about the frequency response experiment and then the results from that, and then compare that to the modeling for frequency response, and then I'll conclude. For the filter wash system, it's a simulation of the filter wash. Our team, like the buff team, also worked with both these valves closed for the entire time. This is basically a basic block diagram for the filter wash system. Something I'm going to throw up here real quick because my rest of the slides don't illustrate it well. Once we spoke about in the past, the input would have been a step response. And what I'm going to be talking about today is going to be some sort of sine input. And on this side, the output, you are familiar, we'll go with like this. And once again, we're going to get an output. So that's just sort of general. That doesn't very specifically talk about the various experiments, but I just want you to know what I'm talking about. This is it's the previous work done. It was a steady-state operating curve for the step response. We found our output to be equal to approximately 6/10 of the input. Now for the frequency response experiment, which I'm primarily going to be talking about today, the input is a sine function at a variety of different frequencies. And our goal was to observe the amplitude ratio and the phase angle. And then after we had done that, find a few different values for the system, including the gain for the system, the ultimate frequency, and the KCU. So, what you can see here is the frequency response. And from this plot, we are going to measure some values that are going to be used to determine the amplitude ratio and the phase angle, primarily T, the small t, delta m, and delta c. Note that delta m and delta c can also be determined this way. In some respects, it's a little more visually pleasing, but you're still going to need this plot to get your information for your phase angle. And that brings us to this. This is how we interpret those plots. Once you have determined for each frequency your delta c, your delta m, and your t's, you can determine an amplitude ratio and a phase angle for each frequency. We did this for a variety of frequencies. And this is a brief table summarizing those results. Now the important part is we're now going to plot both the phase angle and the amplitude ratio against the frequency, and that will allow us to read a few important values from the Bode plots. And this is how that's done. If you look up here, you can see the ultimate frequency, the K, the KCU, and the order can be determined by reading these plots as indicated by the red arrows. Reading this plot for the system, the numbers we come up with was a gain of 0.85, ultimate frequency of 0.65 cycles per second. The order was approximately first order, and the time constant was approximately 0.46 seconds. And now this is going to get compared to modeling the frequency response. These are the key formulas used to do that. And what you wind up with is you're going to manipulate these three parameters in order to essentially lay your model amplitude ratio and your model phase frequency on the same Bode plot over the experimental values. And by manipulating, I'll go back here a second, by manipulating these three values, you'll get an overlay until they match. And the model results for those were K of 0.75, a time constant equal to 0.39 seconds, and a dead time of approximately 3.4 seconds. And just to conclude, the frequency modeling and the frequency experiment were reasonably close, but not entirely. to repeat with 0.75 pounds per minute per percent was the gain using the modeling, and with a time constant of 0.39 seconds, and the experiment we had a value of 0.85 pounds per minute per percent with a gain and a time constant of 0.46 seconds. Any questions?